Hey everyone, and welcome. Today we're heading to the town of Digitville to solve a fun little mystery called The Two Sneaky Numbers of Digitville. It sounds like a storybook, but it's actually a really interesting Leetcode problem. Let's dive in and see what it's all about. Alright, so here's the situation. Imagine a town has a list of numbers. This list is supposed to contain every number from 0 up to some value, let's say n-1, exactly one time. So if n was 5, the list should be 0, 1, 2, 3, 4. But things have gone a bit wrong. Two numbers have snuck into the list an extra time. So instead of every number appearing once, we have a longer list where two numbers now appear twice. Our job, as the town detective, is to figure out exactly which two numbers those are and return them. Let's walk through an example to make this concrete. Say we're given the list 0, 3, 2, 1, 3, 2. First, let's figure out what the original, perfect list would have been. Our current list has 6 numbers. Since we know 2 are extras, the original list must have had 4 numbers, which means it was the list 0, 1, 2, 3. Now, we just scan our given list. We see a 0, okay, a 3, okay, a 2, then a 1. All fine so far. Then we hit another 3. Gotcha, that's one of our sneaky numbers. And a moment later we see another 2. That's the second one. So our answer is 2 and 3. Just a quick heads up. We'll be walking through the solutions using Python. But don't worry if that's not your main language. The logic is what matters, and I'll be showing the full code for Java, C++, and JavaScript towards the end of the video. Okay, let's think about our first approach. When you hear count how many times something appears, what's the first data structure that comes to mind? For most of us, it's a hash map or a dictionary. We can just walk through the list of numbers, and for each number we see, we'll add it to our map and increase its count. After we've gone through the whole list, we just look at our map and pull out the two numbers that have a count of 2. Simple and effective. Okay, we've talked about the big picture and the logic. Now let's see what this looks like as actual code. I'll put the full solution up on the screen first. And don't worry, after that, we'll walk through the most important sections together. Alright, here's the Python code for our hash table approach. As you can see, it's pretty concise and directly follows the logic we just discussed. Let's break it down piece by piece. First up, we initialize an empty dictionary called count to store our frequencies, and an empty list called res, which will hold our final answer. Then, we start a loop that goes through every number, which we'll call x, in the input list nums. Inside the loop, we update our count dictionary. The line count.get x0 is a neat Python trick. It says, try to get the current count for number x. If you can't find it, just assume it's 0. Then we add 1 to whatever value we get back. Once that first loop is done, our count dictionary has a perfect tally of every number. Now we just need to find the sneaky ones. We start a new loop, this time iterating through the keys in our count dictionary. For each number x, we check if its count is equal to 2. If it is, we've found one of our sneaky numbers, and we append it to our res list. After checking all the numbers, we just return the res list, and that's our answer. Okay, now for a really clever method that uses bitwise operations. This one feels a bit like magic at first. The key property we're going to use is that any number XOR'd with itself is 0. Think about it. All the good numbers appear once in our input list, and once in the ideal list from 0 to n-1. The two sneaky numbers, however, appear twice in our input list, and only once in the ideal list. So if we XOR everything together, all the numbers in our list, and all the numbers from the ideal list, what happens? All the good numbers cancel out, leaving us with just the XOR of the two sneaky numbers. So now we have a single number that's the result of sneaky 1, XOR sneaky 2. How does that help? Well, since the two sneaky numbers are different, we know this result isn't 0. That means at least one of its bits must be a 1. And if a bit is 1 in the result, it means that the corresponding bits in sneaky 1 and sneaky 2 must have been different. This is the key. We can now use this one differing bit to split all of our original numbers into two groups. One group where that specific bit is set, and another group where it's not. And we know for sure that our two sneaky numbers will end up in different groups. This bitwise logic can be tricky to wrap your head around, but the code is surprisingly compact. Let's take a look at the full implementation, and then we'll walk through how it pulls off this clever trick. Alright, here is the full Python code for the bitwise approach. It might look a little dense with all the XOR symbols, but it's just following the steps we outlined. Let's go through it. First we figure out n, which is the length of the original, perfect list. That's just the length of our input list minus 2. We initialize a variable XOR underscore sum to 0. Then, we do exactly what we talked about. We loop through our input list nums and XOR every number into XOR_sum. After that, we loop through the ideal range of numbers, from 0 up to n, and XOR those into XOR_sum as well. At the end of these loops, XOR_sum holds the value of sneaky 1, XOR sneaky 2. Now for the magic trick. We need to find any bit that's set to 1 in our XOR_sum. A common and super efficient way to do this is to get the rightmost 1 bit. The expression XOR_sum, bitwise, and with the negative of XOR_sum, does exactly that. We store this value in a variable called low bit. This low bit will be a number like 1, 2, 4, 8, and so on. It has only 1 bit set. We also initialize 2 variables, x1 and x2, to 0. These will eventually become our 2 sneaky numbers. Finally, we repeat the process, but this time with our low bit separator. We loop through nums and the ideal range of numbers again. For each number, we check if its bit at the low bit position is set. We do this by taking the number and doing a bitwise AND with low bit. If the result is not 0, it means the bit is set, and we XOR that number into x1. If the bit is not set, we XOR it into x2. After we've gone through all the numbers, x1 will hold one of the sneaky numbers, and x2 will hold the other, because everything else will have cancelled itself out within its own group. We then just return them in a list. If bitwise operations aren't your cup of tea, there's another clever way to solve this using some basic algebra. Let's call out 2 sneaky numbers, x and y. Think about the sum of all the numbers. If we take the sum of our input list and subtract the sum of the ideal list from 0 to n-1, what's left? Well, it's just x plus y. We can do the same thing with the sum of the squares of the numbers. The difference will be x squared plus y squared. Now we have a classic system of 2 equations with 2 variables, which we can solve to find x and y. The math might sound a little intimidating, but just like the bitwise solution, the code to implement it is quite straightforward. Let's pull it up. Here's the Python code for the math-based approach. We'll need the math library for the square root function, but otherwise, it's all basic arithmetic. Let's break down how we get from the sums to the final answer. First, we find n just like before. Then we calculate the 2 sums we need. Sum 1 is the sum of our input list. Sum 2 is the sum of the ideal list from 0 to n-1, which we can calculate directly with the formula n times n-1, all divided by 2. We do the same thing for the sum of squares. Squared_sum1 is the sum of each number in our list squared. Squared_sum2 is the sum of squares for the ideal list, which also has a known formula. Finally, we find the differences. Sum_diff is our x plus y, and squared_sum_diff is x squared plus y squared. Now for the final step, solving the equations. Through some algebraic manipulation, we can find the difference between x and y. The formula for this difference, which we'll call diff, turns out to be the square root of 2 times the squared sum difference, minus the sum difference squared. It looks a bit complex, but it's just a direct formula. Once we have the sum of x and y, which is sum_diff, and the difference between x and y, which is diff, finding them is easy. X is their sum divided by 2, and y is their difference divided by 2. We calculate those, and we have our answer. So how do these 3 approaches stack up? In terms of time, they're all pretty much the same. They all need to look at every number in the list at least once, so they all have a time complexity of big O of n, where n is the size of the input list. The big difference is in space. The hash table approach needs extra memory to store the counts, which could be up to O of n, in the worst case. But the bitwise and math approaches are fantastic. They only use a handful of extra variables, giving them a space complexity of big O of 1, or constant space. Alright, that covers the main solutions in Python. As promised, for those of you who code in other languages, I'm about to show the full solutions for Java, C++, and JavaScript. I won't be breaking these down, so just pause the video on your language of choice to check it out. Alright, as promised, here is the full solution for the hash table approach in Java. You can pause the video here to take a closer look at the implementation. Next up, here is the C++ version of the solution, also using a hash map, which in C++ is called an unordered underscore map. Again, feel free to pause and review the code. And finally, here is the solution in JavaScript, using its built-in map object to handle the counting. Hopefully, seeing it in a few different languages helps solidify the concepts. So let's wrap it up. We looked at 3 great ways to solve this. The first, using a hash table, is the most intuitive and direct. The other two, using bitwise operations and math, are more advanced but incredibly efficient in terms of memory. It's a fantastic example of how there's often more than one way to tackle a problem, each with its own trade-offs. Alright, before we jump into the other languages, I want to quickly show you a personal project I built to solve a problem that always drove me crazy. It's an app called My Daily To-Do. My biggest frustration with every other to-do app was retyping the same things every single day. Go to the gym, review code, work on the daily Leetcode problem. You know the drill. So, I built my app around one simple but powerful idea: separating your routine tasks from your one-off tasks. Routine tasks, marked with the little refresh icon, automatically reset for the next day. One-off tasks, like ship new feature, get the little puff of smoke icon, and they disappear for good once you're done. This small change turns a dumb checklist into a smart scheduler. If that sounds useful, you can try it right now on the web. The link is in the description. And one more thing I want to make super clear. Right now, as a thank you for being an early supporter, the app is 100% free. There are no ads, and no subscriptions whatsoever. This means you get access to everything, including really powerful features like presets, which let you save entire task lists and load them with a single tap. Now, down the road, creating new presets will likely become part of a premium plan to help support the channel. But, and this is the important part, any presets you create now, while it's all free, are yours to keep and use forever. So it's the perfect time to check it out on the web, play with all the features, and build out your perfect setup at no cost. If you enjoyed this problem and want to keep practicing, the learning doesn't have to stop here. I've organized all my video solutions into handy playlists. Whether you're looking to grind through more Leetcode easy, medium, or hard problems, or you want to master a specific topic like sliding window or dynamic programming, I've got a playlist for you. It's the perfect way to focus your study sessions. Go to the playlist tab and find a playlist that fits your goals. Also, if you're looking for even more Leetcode problems beyond the daily challenge, I've started a second channel called Leetcode Unlocked. It's where I'll be posting solutions to a ton of other problems, so if you're serious about your interview prep, be sure to check it out. The link is in the description below. Hope this Leetcode solution breakdown made sense. If it helped, give that like button a click, maybe subscribe for more, or drop a comment if you have questions. Make sure to turn on the notification bell so you know straight away when I upload a video, because I upload videos daily. If you want to support the channel, a few people have asked how I plan my solutions. I'm a big fan of sketching out the logic and data structures on a tablet before I code. It really helps. I've put affiliate links in the description to the tablet I use and a few other good options. Using those links doesn't cost you anything extra but really helps me out. Or, if you're feeling generous, there's always the Boba Fund. Keep coding, and I'll catch you in the next one.